Hey, so far all of the substitution problems we've looked at have been with indefinite integrals. I'd like to take a look at substitution with definite integrals. Let's consider the integral from 0 to 2 of x over x squared plus 1 with respect to x. We start it the same way we would do a substitution problem with an indefinite integral, make up a new variable r, we'll set it equal to x squared plus 1. So that dr is 2x dx, and we don't have a 2x dx, but we do have an x dx, so we can divide both sides by 2 and get that 1/2 dr is equal to x dx. Okay, there are two different ways to do these problems, and they both start with these same opening steps that we've just done. I'll call them method 1 and method 2, but you should understand that that's just what I'm calling them. The world doesn't agree that this one is method 1 and this one is method 2 or anything like that. They don't have their own particular names. Method 1 is conceptually very straightforward. It says that you already know how to compute definite integrals. To do it, you compute the indefinite integral, and then you evaluate at the endpoints. And so, using substitution, the indefinite integral, x over x squared plus 1 with respect to x, is equal to the integral of 1 over r, that's the 1 over x squared plus 1, and what's left is x dx, and that's equal to 1/2 times dr. And so we get 1/2 times the integral of 1 over r dr. That's an easy integral. You get 1/2 the natural log of the absolute value of r plus a constant. And since r is x squared plus 1, that's 1/2 the natural log of the absolute value of x squared plus 1 plus a constant. Now what we've done is computed the indefinite integral. All that's left to do is to compute the definite integral. And to do that, you can take any indefinite integral. In particular, we can take the one where the constant c is 0 and evaluate it from 0 to 2. And so we plug in 2 and we plug in 0 and we start doing the arithmetic. And we end up with 1/2 the natural log of 5 after observing that the absolute value of 5 is just equal to 5 and that the natural log of 1 is equal to 0. That was the first method. The second method, a little bit slicker. It says instead of turning the definite integral into an indefinite integral, we keep it as a definite integral in terms of the new variable r. The problem is that these constants of integration 0 and 2 are values in terms of the variable x, and we need them to be values in terms of the variable r. And so the first step with the second method is to change those constants of integration into values that make sense for the variable r. And we use the fact that r is x squared plus 1 to determine that when x is 0, r is 0 squared plus 1, or 1, and when x is 2, r is 2 squared plus 1, which is 5. So that the integral from 0 to 2 of x over x squared plus 1 with respect to x becomes 1/2 the integral from 1 to 5 of 1 over r dr, where the 1/2 and the 1 over r dr come from the same substitution that we did over here. We got that this integral, this indefinite integral, was equal to 1/2 the integral of 1 over r dr. That's the same thing we have here, and it all comes from the fact that r is x squared plus 1, and x dx is 1/2 dr. And the true beauty of this second method is that's a very simple definite integral. You compute it and you get 1/2 the natural log of the absolute value of r evaluated from 1 to 5. Which is, of course, 1/2 the natural log of the absolute value of 5 minus 1/2 the natural log of the absolute value of 1. And as you can see, we've already worked that out. It's not difficult. You simply get 1/2 the natural log of 5 after observing that the absolute value of 5 is 5 and that the natural log of 1 is 0. Okay, that's it, and I'll give you one to try in just a second, but first I would like to show you some very common mistakes never to make. This is where the horror really starts. It's basically a matter of combining the two methods. You have a choice. You can either do an indefinite integral, in which case you leave off the constants of integration altogether. That's the first method. Or if you're going to do a definite integral, like the second method, then you have to change the constants of integration into values that make sense for the new variable. In particular, this 0 and this 2, totally wrong. It is the integral from 0 to 2 of x over x squared plus 1 dx, absolutely not equal to 1/2 the integral from 0 to 2 of 1 over r dr. So never do that. Just to see where people tend to go with that, it is true that 1/2 the integral from 0 to 2 of 1 over r dr is equal to 1/2 the natural log of the absolute value of r evaluated from 0 to 2. It's just that that's not equal to the original integral. In fact, if you evaluated that, you'd have to plug in natural log of 2 minus natural log of 0, and there is no natural log of 0. The natural log is not defined at 0. And then people tend to turn the r back into an x. And so the unfortunate and maybe somewhat interesting thing here is that you can come up with the right answer, 1/2 the natural log of 5. The problem is that 1/2 the natural log of r evaluated from 0 to 2 is absolutely not equal to 1/2 the natural log of x squared plus 1 evaluated from 0 to 2. It's equal to 1/2 the natural log of the absolute value of 2 minus 1/2 the natural log of the absolute value of 0, which doesn't even make any sense because the natural log is not defined at 0. And so what's really happened is, by making 2 mistakes, you've gotten to the correct answer. So don't think you get full credit for that. You lose plenty of points for making 2 mistakes. And so make sure you don't combine the 2 methods. Either do an indefinite integral, come up with some antiderivative in terms of the original variable x, and then evaluate that from 0 to 2. That's method 1. Or turn your original definite integral into a new definite integral, but also fix the constants of integration so that they make sense for the new variable. That's method 2. Okay, you try this one, use either method or use both if you like. We'll do it both ways in just a moment. Don't let the pi scare you. It's just a number a little bit bigger than 3. You do this the same way you would as if it said sine of 7x. In particular, it is a substitution problem. If this had just been the integral of the sine of x, you could do it without substitution, but it's not. It's the sine of pi times x. So let your r equal pi times x, and go from there. Pause the video, work it out, and when you're ready, start it up again, and we'll do it together. Both methods start the same way. We let r equal pi times x, so that the derivative dr dx is just equal to pi, and in differential notation, that means that dr is pi times dx. We don't have a pi times dx, we just have a dx. So if you divide both sides by pi, you get 1 over pi dr is equal to dx. For the first method, we just compute an antiderivative, an indefinite integral. The sine of pi times x is the sine of r, and dx is 1 over pi dr, and I've pulled the 1 over pi outside the integral. That's an easy integral. The derivative of the cosine is the negative sine, and so we need the negative cosine to be the antiderivative of the sine. And so you get negative 1 over pi times the cosine of r plus a constant. And turning that back in terms of the variable x, we get negative 1 over pi times the cosine of pi x plus a constant. We're now ready to compute the original definite integral. The integral from 0 to 1 of the sine of pi x dx is just the antiderivative that we just came up with, evaluated from 0 to 1. You have to remember a little bit of your trigonometry. The cosine of pi is negative 1. The cosine of 0 is 1. You have to also be careful with your negative signs. And in the end, you get 1 over pi plus 1 over pi, which is 2 over pi. Method 2 starts the same way with the same substitution. R equals pi times x. You still get 1 over pi dr is equal to dx. But now we have to turn the constants of integration 0 and 1 into values that make sense for the new variable r. And we find that when x is 0, r is also 0, and that when x is 1, r is equal to pi. And that lets us write the original definite integral in terms of a new definite integral. It's 1 over pi times the integral from 0 to pi of the sine of r dr. That's an easy integral. You get 1 over pi times the negative cosine of r evaluated from 0 to pi. And as before, remembering your trigonometry and being careful with your positive and negative signs, you end up with 1 over pi plus 1 over pi, which is still 2 over pi. You're welcome to learn either or both of these methods. As I pointed out, I think the second one is a little bit slicker, but there will be times when things get a little complicated, in particular when we're doing integration by parts, which is our very next technique, where method 1 is probably the easier one to do. It's certainly conceptually easier, and I think if you have to pick one of them, pick method 1. Method 2, not that much harder and sometimes easier. Personally, I would learn both, but I leave it up to you. Okay, that was substitution with definite integrals. There is, of course, a homework assignment on it, so take a look at that, give it a try, come to class with any questions, and I will see you soon. Bye.